We're all familiar with games like chess or your favorite sport. Scientists and mathematicians can actually study games and the most efficient way to play them. But what if we applied those principles to things like markets or the weather? Meet Max Fishelson, a computer scientist and game theorist at MIT who is doing exactly that.
Hey everybody, my name is Max. I'm a fifth year PhD student here at MIT. I study computer science. I'm technically in the computer science department. But I actually do, my research is in kind of an interface between mathematics, computer science, and economics. Specifically, what I study is known as game theory. Um, so what is a game? I guess you've heard the word game before. Game can refer to a great many things, right? A game could be like rock, paper, scissors, could be like chess, could be a sport, could be a game, could be a video game. These are all games. What is a game in the most general way we could state it? A game is going to involve some collection of players or agents. Each of them is going to take some action, and then each of them is going to receive some outcome, right? That is, a big umbrella that all of those games and many more things fit under. And a lot of scientists will study games, right? So, again, right? So like rock, paper, scissors falls under that umbrella, right? We'd have two players. Each of them takes an action, and then each of them receives an outcome. Cool. You could also have like a video game, right? You have, several players. Each of them chooses some action, and then they each receive some outcome, right? But this generic format is something that applies very much more generally. It can apply to the study of markets, for example. Let's say we have a farmer's market. So we have a bunch of players who are the farmers. Each of them takes an action, which is maybe setting the price on their carrots. And then they each receive an outcome, which is, okay, this is how many customers they received. And so the study of games, the study of these situations where you have multiple agents who all make a choice, and then somehow, as a function of their choice, each of them receives an outcome. And my outcome is a function of everybody's choice. And there's interlocking choice here. That is a very generic thing. And understanding games can, right, it can help you play chess better, but it can also help you understand markets better, which is what economists are very interested in. Self-driving cars, a big problem in making cars drive themselves is understanding it's a game, right? You have cars on the road, and like my choice as a car is going to impact your choice as a car, and we're going to be, so artificial intelligence. Nowadays, you have AI, and they're interacting with other AI, and that constitutes a game. So, very broadly speaking, there's a lot of scientific interest in understanding games, understanding, different aspects of them, understanding how to play optimally in games, and that's what I do from research. And specifically, something I'm interested in is the task of calibration. Okay. What is calibration? If you ever look at a weather report and you see these like, percent confidence intervals and like, oh, today 60% rain, 30% rain. This is algorithms. I study algorithms that what's an algorithm? An algorithm is a piece of computer code to help you make a decision. So, previously, we have people making decisions, right? Choosing something. Nowadays, people use computers to make decisions, right? They had put all their data into the computer, and the computer's like, let's do this. So that's what an algorithm is, a piece of computer code where you give it some input and it tells you something, it suggests what action to take. And so what I study is algorithmic game theory, which is the computer is helping you make a decision in a game against other computers, and you study the dynamics of that situation. So I've been working on calibration, and essentially, like through my research, we've boiled the problem of calibration, giving accurate forecasts, down to this very simple game known as the plus minus game. Okay, and I want to play the plus minus game with you. And it's not going to be immediately obvious what's the connection. We'd have to go through some mathematics to see what's going on there. Um, but this is a cool game, and I wanted to give y'all a little peek into my world. My life is essentially trying to study this two-player game. So what's the plus minus game? Okay, it's like a board game. It involves the following. We're going to have some number of spaces. Okay, let's say 5 spaces. Okay, and there's going to be 2 players in the game. There's going to be a pointer player and a label player. So I'll be the pointer player. Fatima, would you volunteer to play as the label player? She's nodding. Cool. All right. So how does the game work? We're going to repeatedly go back and forth and have the following interaction. So I am going to point at one of the spaces. And then Fatima, you're going to say plus or minus. So go for it.
Plus.
Plus. So she said plus, and so we put a plus in that spot. Okay, pretty straightforward. We're going to repeatedly do this. And the game ends when there are either 3 pluses or 3 minuses in the board. Okay, so if 3 of these spots. And essentially, as the pointer player, I want the game to end as soon as possible. I am trying to get either 3 pluses down or 3 minuses down. Fatima, as the label player, is trying to prevent this from happening for as long as possible. Okay, that's the basics. Now there's a catch, okay? The catch is the following. Let's say that this is what the game board looks like. We got some pluses here and here. And let's say I point here. Well, one of the rules of the game is if there are ever pluses to the left of my pointer, they're going to get deleted, okay? So those go away. Similarly, if the game board looks like this, and I ever point to the right of minuses, those minuses get deleted. Okay, so intuitively, that is counter to my goals as the pointer player. I'm trying to get a bunch of pluses and minuses down because that's how I win the game, once I get my 3 pluses and 3 minuses. However, sometimes I'm forced into a spot where I have to delete signs, and then that's not ideal. Cool. So let's play the game. All right. So let's do it from scratch here, and we'll play it for real. All right, Fatima. I'm going to start by pointing in the middle here. Your action.
Plus.
Plus. All right, put a plus. All right. Now I'm going to move over to here. Boom. Yeah, that's right. All right, go for it, Fatima.
Minus.
Minus. Nice. All right. Now, what I'm going to do, here you'll see, Fatima has successfully put me into a spot where I have to delete a sign. If I pointed over here, I'd lose the minus. If I pointed over here, I'd lose the plus. But sacrifices may be made. So I'm going to point here, and that's going to delete this plus. But now, Fatima, it's your turn.
Plus.
Plus. Cool. Nice. Now I'm going to point into the middle.
Minus.
Minus. Good choice. All right. Now I'm going to point way over on the end. Now, again, I pointed here, so we lost the plus. Unfortunate. Go for it.
Plus.
Plus. She had to go plus, right? So if you went minus there, the game would have ended because I would have gotten 3 minuses. All right. Now I'm going to point here.
Plus.
Got to go plus. Again, 3 minuses would have cost you the game. All right. Now I'm going to point way over here. And again, that's going to delete both of these minuses. I've lost a lot of progress on that one, but it's okay. Go for it.
Minus.
Gotta go minus. Already 2 pluses down. Now I'm gonna point here.
Another minus.
Gotta go minus. And now the moment you've been waiting for, I point at the middle.
So either answer I give you will end the game.
The game's over. We've ends here. So no matter what, plus or minus, I've achieved my success of getting 3 pluses or 3 minuses down. Wonderful. So that was the plus minus game. And what did we just do? We just played the plus minus game with 5 spaces. And game over was at 3, right? Either 3 pluses or 3 minuses. And if you were counting, that took exactly 9 rounds. And that is actually the optimal length of the game. whether like both me and Fatima made the best possible choices. If I made any worse choices, it would have taken longer. If she made worse choices, it would have taken better. But a mystery to science, so that's understood when there's five spaces. A mystery that no human on Earth knows is what if we played the plus minus game, but with a billion spaces? And the game over condition is a million. How much time does this take? So nobody knows. And I'm not talking about, what's the exact number. Like, I'm not talking about, oh, it's exactly 1, 2, 3, 4, 5. I'm talking about what is the rough order of magnitude? Like, am I going to get about a million down? Answering these questions, studying the behavior of this game as the plus minus game grows and grows is a big mystery because it ties to the problem of calibration and it ties to all these other scientific things. So essentially, this is like what my job is, right? It's involving taking like complex real world scenarios, trying to boil it down into something very fundamental, like just understanding the dynamics of a two-player game, and then studying the game, trying to repeatedly. I mean, essentially every day I wake up and I come up with like a strategy for the pointer player, and then I come up with a strategy for the label player that does even better. That and I come up with a strategy on a pointer player that does even better. And I keep trying to improve these strategies until I understand what is the optimal strategy in this game. And that is helping make scientific progress. So, calibration, let's say that you're a weather person. Every day, you got to predict, is it going to rain or not? So, every day, you come up with a prediction, and then it is revealed to you whether it rains or not by the clouds. So on the first day, let's say you predicted 20% and then it rained. Cool. We repeat. On the next day, you give some new prediction and then we observe whether or not it rains. And we do this over and over for, let's say, capital T days. Let's say it's like 1,000 days. And your goal to be calibrated, what you would hope for, is that if you looked back on all the days that you said 20%, it rained on about 20% of those days. If you look back at all the days you said 30%, it rained on about 30% of those days, et cetera, et cetera. So this is the task of being calibrated. And interestingly enough, this can be viewed as a game because you could view it as a game between a forecaster, so that's you, given the predictions, and also a second player who's choosing the weather, right? So here's one person who's given these percents. Here's another person who's like saying, all right, today it's going to be sunny. Today it's going to be rainy. And so understanding can you be calibrated boils down to understanding this game of can, I give predictions in such a way that whether this person comes in, whatever they label it with, like who wins this game? Does the weather person win this game or does the forecaster win this game? And it boils down to the sign, to the plus minus game because you're studying like you can imagine the spots. Okay, it takes a good amount of mathematics to get the full boil down, but it's roughly that like the different spots correspond to different predictions that I could give as the forecaster. The labels correspond to whether plus or minus, and so that's all I got for you today. If you want to understand that connection more or play some games or anything else, you just ask me.
Thank you so much, Max.
Yeah.
Okay, let's kick off the Q&A. So I'm curious, part of what you described is that, you're waking up every day and you're trying to come up with these strategies. And that's, this is an iterative process and it keeps on going. I notice a big board of equations and math behind you. Is this something that you're doing sort of all the time? You have a blackboard at home?
That's my roommate. So I live with I live with three other grad students. I think this is his one of my friends Rahul's physics homework. So
Oh,
this I don't usually work from home. I usually go into the office, but it's spring break.
oh,
But
right.
yeah, blackboards. That's a good depiction. A lot of if you go to the office, which is where I work, the Stata Center. There's on the fifth, sixth floors. There's like whiteboards everywhere, and you'll have students walking around chatting about math and stuff, which is fun because math's cool.
Yeah,
Yeah.
that's wonderful. And then kind of that leads me to the next natural question. Can you just describe for us What does a typical day look like for you working on these problems? So you already mentioned you work from the office, but what's your routine like?
Yeah, I mean, I get up, I got my apple here. Got to get your fiber, very important. And then I went to the office. I mean, yeah, so I have, I guess, about three problems that are like my main problems in circulation. One of them is understanding the sign flipping game, the plus minus game, sorry. One of them is trying to study this old economic theory known as Blackwell's approachability theory, because again, right, algorithmic game theory. So game theory started as an economics thing, like let's study how these markets work, and now it's a computer science thing. So it's how do computers in a environment interact with each other. So a lot of the work is like going back to like old economic theories and trying to revitalize them and then map them to the world of computer science. But yeah, I've got like three math questions I'm cycling through. They usually take several months or years at a time to solve, but that's okay because you enjoy it. It takes a lot of patience. If you're like, I want to solve the math problem now, then it's not going to work out because it's going to take a long time. So it's just about the process of like holding on to the fun of like, hey, this is a cool puzzle that I'm working on, and that's what I get to do for my job, and that's a gift, and I'm grateful for that. And yeah, so I just wake up, I'll eat my apple. I'll decide like, okay, today I'm feeling like working on this math problem. I'll just kind of sit there and do it. I've got some collaborators. I'll call my friends. We'll chat about new ideas. And you just kind of keep trying new ideas and you're exploring different pathways of finding proof that certain things are true. Yeah.
Got it. We have a question from Ellie from Boston, and Ellie's wondering, what's your favorite game?
Hey, Ellie. My favorite game? I really like Settlers of Catan. That's a fun game. I like the that you can move the hexagons around. Um, there's a game I enjoy a lot called anti-chess. That is essentially you set up the pieces like chess, but then the goal is to lose all of your pieces. Uh, the rule is if you can attack a piece, you have to, and then your goal is to actually like pull your opponent in to take all of your pieces. Those are two board games I enjoy a lot. Yeah.
And are you thinking of game theory and what you're doing for your PhD when you play these games?
So I mean, I guess like uh right, game I'm not like studying game theory doesn't mean you're like the best gamer on earth, I think like there's people who specialize in I'm gonna get really good at this one game, like I'm gonna get really good at chess, whereas game theory is more like zooming out, right? Like we said, we were talking about all these games at the start, but we put them all under this umbrella of these are just multiple people, they all make a choice and then they all receive an outcome, right? And so the goal isn't to like necessarily study one specific game. Okay, though it is that is the scenario in this particular research problem. Um, it's usually just like understanding the structure of games as at a large, like rather than like how does learning in games? How do we find like optimal strategies in games generally? Like what is a general strategy we can do to like compute optimal strategies? Yeah,
Got
stuff
it.
like that.
Okay, so we have a couple of questions about some of your past experiences that led you to study games. So before I ask those questions from the Nord Anglia students, I wonder if you could tell us, how did you come to study this in the first place?
Game theory? I mean, I took it as an undergrad, I guess. I went to MIT as an undergrad too. So I'm now in my, I guess, ninth year at the institute. Uh, and I guess when I was in undergraduate, third year, I was kind of seeking direction in life. I was like, what should I do? Like, what's a cool thing to do? And then I took this class, algorithmic game theory, which was taught by Professor Kostis Daskalakis. And I was like, this is the coolest math I've ever seen in my life. Like, like it was just like there was like a point where like he would like finish this proof and like everyone like stood up and just like clapped because they were like that math was awesome. So yeah, y'all watching. A lot of you are in middle school, maybe high school. So a lot of the early stages of math are do involve a good amount of memorization. It's like, okay, let me memorize the multiplication table and then just multiply, multiply. Okay. And then you're going to get to high school and it's going to be, let me memorize this equation. Let me memorize the quadratic formula and then just apply, apply, apply the formula. Okay. So that's the early stages of math. Is kind of formulaic. But if you get through that, if you get to the other side and you start taking some math classes when you get to college, it gets a lot more creative. Okay. It's a lot more about synthesizing all of these tools that you've picked up from all the different little math classes and using them to solve puzzles. Okay. Using them to understand the sign flipping game, the plus minus game, using them to study all of these different things. So I encourage you to hold on. Right. The frontier of math is one of the coolest things to explore. I very much enjoy doing it. It's my dream job. But you have to learn all this stuff, right? I had to get the algebra under my belt. I had to get the geometry under my belt. And now, so, there's going to be a lot of time spent, just kind of accumulating knowledge. And it's going to be like, all right, what's this all for? I'm just memorizing formulas. But the point is that once you have that toolbox, then you can go forth and it involves more creativity. It's involved like mathematics gets more and more creative the further along you go. I encourage you to stick with it. I stuck with it to the point that I took this class in undergrad that was really cool called algorithmic game theory. I fell in love with the class. I went to the professor. I was like, hey, man, we should do research. You're pretty cool. And then we started working together. And then we started discovering some stuff about the world. And then he was like, you know what, Max, you can be my PhD student. And now I'm still at MIT.
Okay, well, that's wonderful. So you've given us some elements of that background, and I think it's amazing that, we're encouraging folks stick with learning those fundamentals and basics, and then you can start to apply them to really cool problems like this. So Lilia and Ariana and Nico are both wondering, what sort of classes did you take in high school that kind of prepared you to continue studying math in college and eventually work on these problems? What classes do you recommend? Let's say someone is trying to select their classes for the last 2 years of high school. What should they be taking?
Hi, Ariana and Nico. Let's see. High school, I mean, I didn't have a lot of freedom in high. I guess once you go to college, you have a lot of there's just a list of 1,000 classes. It's like, hey, take any four you want. So that's pretty cool. Personally, I didn't have a lot of freedom of selection in high school. Had to just do, I guess, geometry in first year, and then algebra two, trigonometry, and then calculus. That was kind of the prescribed thing. Those are all cool maths. Calculus will help you understand the real world, and physics is all about calculus. It's all about dividing down to very small units. Like I'm imagining this apple is actually composed of a continuum of points instead of like a billion different little atoms. Things like this. So I'm not sure. What classes are you choosing between? I can help you choose one.
I think it maybe was focused on mathematics, so you went ahead and answered that there is a certain pathway that you take in terms of the ordering of the math classes
Yeah.
before you get to college, before you have
Geometry is fun. Geometry is cool because it's your first introduction to proof, right? So that's essentially what I work on, right? So there's maybe if you're in middle school, elementary school, you're just doing formula, right? It's just like 9 times 5, right? 45. You're going through. Geometry is usually most people's first introduction to proof, which is to say that this thing is always true. Like if you have a triangle and you draw the line between this corner, and the midpoint of this side, and you draw these three lines always intersect. Okay, which is funky, right? Usually two lines intersect. A third line doesn't usually have to intersect. It could go through the side here. It doesn't have to, but that's something that's true. No matter what, for any triangle, you give me any triangle, no matter what, these three lines are going to intersect. And so that's what a proof is. It's not here's one specific math problem, solve it. A proof is show that for all triangles, this is true. So that's like the type of math that builds more towards what is like math at the frontier. It's trying to understand what things are universally true. You can view that as a game too, right? A proof is also a game because it's like, okay, the statement I just made is that the three medians of the triangle always intersect. That's what it's called. All right, at the gravitational center of the triangle. So You could do that as a game where one player comes in with a triangle and the other player comes in with a proof. And you see, does this proof prove that this triangle has median intersection? Things like this. Anyways, yeah, that's a
Okay,
cool math to take. I hope you enjoyed geometry.
awesome. We have a question now from Trisha, who's wondering about the process you described where you're thinking about strategies. So Trisha's wondering, do you use any particular algorithms or particular logic to formulate strategies for the pointer player, or is it always trial and error? What sort of math are you applying when you're thinking of those things?
Yeah, so right, it circles back to proof math, right? So, right, what is a proof as opposed to a formula? Is something that's trying to emphasize. A formula is just here's one specific math. Let me plug in a formula. A proof is this should work for all inputs. Like for all triangles, this same argument proves this thing. For all equations, I can run okay. So, what would be the case would be if I was to demonstrate that the pointer player does sufficiently well in the game, I would say that I'm going to create a strategy for the pointer player and then prove that for all strategies of the label player, this strategy of the pointer player does sufficiently well, right? So when you make that's what's called a conjecture, right? A conjecture is something that's not proved. You want to say for all, like here's my strat. I want to say here's my claim, like for all label player strategies, this pointer does great. Okay, so when you have a conjecture, you don't know if it's true. One of two things are true: either it is true, and you have a proof, or it's false. You find a counterexample, right? And so what that would look like is you come up with it's like, I made this statement like for all triangles have this property. And then you'd be like, oh, not exactly, Max. Here's a triangle that doesn't, right? So the process of finding a proof is the same as the process of finding a counterexample. Okay. If I have a conjecture, like this is always true, I repeatedly try to just poke holes in the conjecture. I'm like, wait, that can't be right. What about this? Okay, that didn't quite work. But what about this? All right, that didn't quite work. Okay, none of these are counterexample. And then you eventually either find a counterexample and then say, haha, like you were wrong, Max, your conjecture is false. Or you realize the pattern as to why you keep failing to find a counterexample. And that constitutes a proof. It's like this is the fundamental reason why you can't find a counterexample. So what I have is I produce a strategy for the pointer player, and I want to prove that it always wins. Okay, then what I do to attempt to prove that is to try to come up with label players that defeat, and then I usually end up finding a label player that defeats, and then my new task is proving that maybe this label player always wins the game, and then trying to come up with pointer players that defeat. And then you either eventually stop poking a hole. So this is guaranteed to eventually work because all games actually have an optimal strategy. This is this is like a fundamental theorem of game theory going back to John Forbes Nash in the 1950s, that every game, no matter how crazy or complicated, how many players, how many actions, there is an optimal strategy if you allow for randomness. Let me explain. So essentially, you can think of the game rock, paper, scissors. Okay. Seems like there's no best strategy in rock, paper, scissors, right? Rock loses to paper, paper loses to scissors, and scissors loses to rock, right? So there is no best strategy. However, if I allow for randomness and I randomly, exactly uniformly random, play either rock, paper, or scissors, then there's nothing that you can do in the face of that. I could reveal to you, like Fatima, like I'm going to roll this dice. If it's a 1 or 2, I'm going rock. If it's 3 or 4, paper, 5 or 6, scissors. I could reveal that information to you. Like that's my strategy. And even in the face of that, there's nothing you can do to exploit that. And that constitutes the equilibrium of the game. So essentially, if players continue to improve their strategies over and over, it's not going to just cycle. Like I'm going rock, you're going paper, I'm going scissors, you're going rock. You eventually converge to like optimal play in games, and that's the fundamental theorem of game theory that players will equilibrate eventually.
Got it. Okay, so now I have a quick question for you. Arian's wondering, Max, about the problems you mentioned. You're working on a bunch of math problems. Aryan's
Yeah.
wondering, can you, in a snappy way, tell us what real life problems are they based on?
Yeah, I guess there's this problem of Blackwell approachability, which studies, I guess, so as I stated before, a game has an outcome like win, lose, 1-0, maybe like how many customers did I get in the market? 10. So that's just like a single number. Sometimes real world games involve a multiple number value. It's not just win or lose. It's like, okay, like, I made these choices and then, maybe it was good in this way, it was bad in this way. So what if the outcome of the game is multi-dimensional? That's what that's called. Okay, what if the outcome of the game involves like there's multiple different parameters and I'm trying to optimize many different things at once. So that is what is known as an approachability instance. I guess David Blackwell back in the 1950s studied like whether or not you can always like players in the game can always converge to equilibrium if this value of this game is something multi-dimensional, and it's not always possible, but sometimes it's possible. And recently, I've been studying the problem of understanding whether this is possible when the space of actions is high dimensional. What does that mean? So, if you think of a game like rock, paper, scissors, there's like a small number of actions, but there's three. Modern decision makers have a large number of actions. I have to choose an entire stock portfolio. I can make all these different like choices, and that's my action. Or like if you're playing chess, right? It's like my action is what is an entire total strategy contingency plan for all the possible states of chess. Or if I'm using an AI to make my decisions, then like my strategy is how do I tune and turn all the different knobs of the AI? So modern decision makers, the number of actions you have is immense. Millions and millions of possible. I mean, there's so many things you can do in life. You could do this, you could do this. Like there's usually more than just a finite list. And so I'm studying that. So that question boils down to the following. I can show really quickly. Let's see here. Let's see. Okay, I'll share the screen. So understanding that, I'm trying to understand this shape. Okay, I have this orange circle, and I'm trying to understand the behavior of I guess repeatedly applying this. This thing traces out this shape, traces out this thing, which is called a cardioid. Uh, and this is not meant to really explain anything. This is just like essentially right. The process of doing math research is you're gonna have a very complicated math problem and
Hmm.
then you're going to try to boil it down. Okay, fundamentally, what am I really trying to say? And you're boiling it down until it's just some sort of like simple fundamental like math problem, right? Okay, we've boiled down calibration all the way to the sign flipping game, plus minus game. Sorry, I have multiple names for it. You boil down understanding if black hole approachability can be done in high dimensions just to this one example of I guess this family of maps, which are I'm attempting to visually communicate with that circle spinning around. And then once you have that like fundamental thing that you're trying to that this is the mystery. Like you brush away all the dust and all the feathers, and it's like this is the mystery right here. We just have to look at this one like mathematical object and understand it. And then you do that.
Okay, I'm going to switch gears briefly. We have some questions. Since you mentioned you've been at MIT for 9 years, some of the students are wondering, especially Nico from Boston and Lily from Boston are nearby, and they're wondering what are some things that they, should visit or see at MIT while they're there.
If you come to MIT, I mean, I guess the dome right behind you is pretty cool. That's if you walk along the river. So I guess between the Harvard Bridge and the Longfellow Bridge, which are two bridges across the Charles River. For those not in the Charles River is a river in Boston for those across the world. Um, and Yeah, so you could take that walk. That's a nice walk with your family. There's a nice museum, and you could come check out the Stata Center, which is this funky Dr. Seuss looking building with all these different shapes and walls. And I guess you can access it during the weekdays. On the weekends, I'd have to tap you in. Uh, just let me know. I can give you access. If you want. There's a lot of cool buildings to check out and different like scientific displays
Yeah.
around.
I really enjoy seeing all of the architecture when I get to walk through campus, so I'm sure the Nord Anglia students will enjoy it as well. That leads me into our closing question for today. And this is a Cambridge MIT specific question in a way, so bear with me. So, Megan from Boston wants to know if through your work, you'll be able to help improve weather forecasting prediction, because currently for Boston, they seem pretty poor.
So, okay, weather forecasting is actually an extremely complicated question. Um, to the specifics, so I gave weather forecasting for my specific work. I gave weather forecasting as an example of a calibration problem because it's perhaps a classic example that many people are familiar with, where you're going to be producing probabilities and then receiving an outcome. Really, I guess the plus minus game is for the goal of studying calibration in general. It could be weather, it could be stocks, it could be anything, like any sort of thing that you're trying to predict. Weather specifically is an incredibly complicated question because weather is a chaotic system, which means that what is a chaotic system? It's a system that if you slightly change, have you heard of the butterfly effect? Megan was their name. If the butterfly effect is like, if you went back in time and you like released a butterfly a million years ago and you came back to the present day, then the world would be like fundamentally different because like, one tiny thing could like lead to like a one tiny thing and then like ripple effect. So some systems are very predictable, like the orbit of planets. Okay. So like a planet will make a circle motion. If I like nudge the planet, sorry, so do it in this axis. If I nudge the planet slightly, so it's like a little bit faster, it'll still make a pretty similar path. Like it'll curve like this, maybe a slightly longer oval. But roughly you can like predict like, slight change to the initial condition, roughly the same outcome. Now, that's not the case for more sophisticated center. If you have three planets in space and you nudge one slightly, they're going to eventually start to trace out a totally different path. And weather is like that. So you can look up at the clouds and be like, all right, it's looking rainy. This something very similar to this would be rainy. But actually, if you change like one cloud slightly, it's going to like fundamentally like radically like even a few hours out, it's going to look totally different, right? So that's why weather prediction is such a complicated task, because slight changes to the input are going to radically change the output. There's a lot of modern work on this using machine learning, that is trying to like just crunch as much data as possible and put together better predictions of weather. What I'm trying to work on is the question in the abstract of calibration. It could be hopefully utilized by weather forecasters as a subroutine in their algorithm that's more specifically designed for clouds. It could be used. It's also like, I guess one of the main interests is to make AI more reliable, because sometimes AI will like make something up. It'll be like, yes, like Abraham Lincoln founded MIT in the year like 1200, and it's like that's not quite true. But so essentially, the goal would be also to arm like AI with calibrated. It's like so it'll say report some information and be like, I'm only 30% sure on this one. So that's the other goal.
Got it. Okay. Well, thank you for talking us through game theory, the challenges in thinking about it, all of the strategies, and of course, in an application that, weather forecasting is incredibly complicated. That's why maybe it may not work out every time. But it's a big deal, and we really hope that your abstract work on calibration can be used one day as part of these algorithms and models. And I want to shout out that I'm really excited to see you all next month as well for our abstract cosmic detectives. And with that, I want to thank you, Max, so much for sharing your research with us. I want to thank the Nord Anglia Education MIT collaboration for making this series possible. And I want to thank the students for asking such thoughtful questions and for helping us all learn together today. But thank you so, so much, Max.
Yeah, cheers. Thanks so much for listening, y'all. Hope you learned something new.
Yeah,
All
we all
right.
did. Okay, goodbye, everyone.